Hello participants, welcome you to this course, this module on pointers and problem solving in C programming language. So this course, as you can see, talks about C, pointers and linked lists. Okay, so I presume that a lot of people have difficulties, initial difficulties, when they start working with pointers. I have been teaching this course in different forms, data structures and others, even under QEEE. But then I was discussing C++. Because of an overwhelming demand from your people that C is to be used as the programming language, I am switching over to C for this part of the course. But I'll also like to remind you that when you use C, we expose ourselves to certain properties of this language, and this language is a little loose, a little casual in many things. Because of the reason our programs often get into problems. Okay, so before I formally start, this is the way I would like to conduct the course. I'll talk about pointers. I assume very minimal basics. Okay, so I'll talk about everything about pointers that needs to be dealt with. However, I'll assume that you have reasonable familiarity with other features of C. Okay, so they'll be used, but I'll not be able to discuss too much about them. So since this is a course on pointers, I'm assuming that you people have written programs with pointers for some applications, and I've also got into problems. This course, therefore, I would like it to be a little more interactive. So as soon as I get my screen with your your talk or whatever intermittent inputs on, I would love to be interrupted and ask questions when you have faced some difficulties in the past. So that will help me addressing the course to your needs. Okay. So apart from being interactive, which will help, I'll also use a lot of fragments of C to illustrate, and therefore I may often ask you questions for you to tell me what your answers are, based on which I'll try and see how I moderate it. So let me start with the first slide of the course. This talks about a very small motivation about why I think this course should be done. Okay, so I assume that you are familiar with C and you're familiar with the basic features of C using which programs are written, which are essentially derived data types, arrays, structures and functions primarily. Okay. And to this, when you add pointers, then you get the full power of C. Okay. So I am starting informally initially, and then will become more formal. This pointer data type, and my statement is it's somewhat non-intuitive. Pointers are closer to the machine probably than as compared to the human being. Okay. And therefore it's a little difficult to visualize often what we are writing, why we are writing. The reason therefore is that we often get errors, and most of the errors due to pointers are runtime errors, which are even worse. I'll assume that you know the difference between a compile time error which is pointed out by a compiler when it finds that something is going wrong, versus an error which is at runtime when the program is running and something wrong goes out. So the last line is the catchphrase. We want to make an honest attempt to demystify pointer data type and its use, initially as a data type itself, but on the next lecture, on next Friday, I would like to take up its application. Okay, so I'm recalling here, I'll use some symbols to simplify my job. So maybe I'll use my notes also just to make sure that I can write something and you can see that. I hope you can see this white sheet. Okay, so I'm taking material out from my slide. So basically what we are saying is, if we want to declare a type in C, okay, so what we do is we write something like T of X. So when you write T of X, this capital T is where any legal type of C is permitted, goes here. So what we are going to do today is make sure that apart from the basic data types, which are car, bool, not in C, car, int, short, long, structs, okay, floats. We would like to look at the little more composite type. So for interest for us would be, what do you do when you define an array type, which I'll come in a short while. How do you define an array, which is a collection? How do you define a struct, which is also a collection? This is a homogeneous collection, I'm sure you know. All elements are similar. A struct is a heterogeneous collection, typically. Okay. And then of course we have the basic power of a function to abstract code and write pieces. So all of these are in some sense a new type which are made available by New. So I'll assume this first and last time I'll state it. I hope there is no confusion on this. Whenever we talk about a data type, there are two sets associated, as you can see on the slides. One is a set of values. Okay, the values can be complex in the sense it may be non-trivial values, but they are a set of values. It says a closed set of values, which means you can't reach a value outside of the set V. And the other is a set of operations. So if you know the set of values and if we know the set of operations, then we have defined a data type completely. Built-in data types are already defined by us or by the system. Other types we define for our problem solving. Okay, so this example says that unsigned int on most machines, some of these are also machine dependent, has 2 to the power 32 distinct values. Okay, they actually start from 0 to 2 to the power 32 minus 1 or whatever. And the operator set, which includes addition, modulo and many others, is a well-defined set with well-defined semantics. With this small view of a data type, let's move on, enter the world of pointers. I'm showing you this slide, but I'm not going to say too much except what is important to me. We all know that an array is a collection of homogeneous values. They are set in consecutive locations, okay? And therefore, immediately the use of an array as a pointer comes into picture. So when I define anything, suppose I define int marks, so we know this corresponds to a collection of 10 elements, each of value integer, which are indexed from 0 to 9. I'm assuming you know that. The name of this collection is marks, and you refer to an individual value by working out a subscript, which is the notation, to reach to the ith element of this collection. So why am I bringing it so early here? Because array, which is very well known to be, is laid contiguously in memory. Not now, ever since programming started, Fortran 2, 60s, this has been all the way the same. It is contiguously laid out in memory, which means they are in consecutive locations. In other words, if marks 0 is placed in the location 1000, let's say, just for the sake of discussion, in memory address 1000, then marks 1 is placed in 1004 because int has 4 bytes, my assumption, and so on, and marks 9 also we know where it is. Okay? So it is 1000 plus whatever, so it is 1036. So the addresses are very well known for an array. To whom? To the person who allocates memory, typically the compiler. Why am I saying all this? Because this collection of 10 or 1000 elements are not directly always used for communication. Whenever you communicate an array between functions, you know pretty well that we only communicate the address of marks 0, which is also in C taken as, or even C++, the same as marks, which happens to be, for my example, the memory location 1000. What is then just the name of the array, which does not point to any location? It is the starting address of the entire collection, and as we go along, this is what we will call a pointer. So the name of the array is a pointer. is a great advantage, as we'll see later. It's also a cause of many errors if one is not very sure what marks is and what we can do with this data type marks, which is a point. So coming back to the slide, so immediately after array comes this heterogeneous entity, heterogeneous collection, which in C is called a struct. So since I'm not teaching you struct, I'm just assuming that you know how a struct is defined, which is there on the slide. So what we have defined is a collection of values. The first is an int value, followed by a car value, followed by a car array, followed by a short value and a float value. Okay, this whole thing becomes one type value. So value of a type student will have these 5 distinct components in its value space. What all operations are permitted? I presume you know, so I will not dwell on it now. But if you know C, you know exactly what you can do with this type definition. Remember here, student is just the name of a type. Nothing has happened unless you do something more. What we can do with this student type? So any struct that you define can be subsequently used to create your data, complex data structures. For example, if I have defined student as in the slide, we are empowered now to define, let's say, a student of QEEE C course. Okay, and I can define this of, I don't know how many of you are there, let me make a wild guess, maybe 1,000. Okay, so this defines an array of elements. Each element is a student and the name of the collection as given is of type student. Okay, and you know that in this array I can pick up any element. Well, let's say I pick up QEEE C course, is a very long name, I can see the ith element, and then putting a dot, I can refer to the different fields of the collection, the different objects or entities of this structure. So the only point that I'm trying, since my major interest is pointers, now here again, since it's an array, what is QEEE C course? Just the name of the array. This is also a pointer. It's a pointer to whatever that we look at. So whenever you introduce an array, whether a built-in or over some other data type, you implicitly have a pointer with you. It does not define a pointer. It only says that you have been using the pointer anyway without my saying so. So the next slide is an example. I've given a different example, but in spirit what I just did over there. So I created an array of type student, called it BTech2. Many of you might be BTech2 for all I know. More importantly, this is something again I will not emphasize, but I would like to talk upon. Look at the next program fragment, says float root. Maybe I'll use it here. The only important point which I would like to say here, observe that this is a function. The function has some return value, which is float. It takes 2 arguments. One is an integer value and the other one, I'm sure you have been using it, says it's an array of floats. But actually what we will pass here is just the start address at the call time, because it's an array of the array at call, of some array at the call side. We call this particular function. So effectively what is happening is, even if my coefficient array was 10,000 long, when this function is getting called, we are not passing 10,000 elements, but we are only passing one single value, which is the address of this array. That makes life very simple. Communication time is reduced, okay, but there are other consequences which can arise because of that. This is very important for me. If you want to understand pointers, I'd like to go back to this in spirit. Let's see what is being stated in this particular slide. It says that whenever you declare or define an entity, it could be an integer, it could be a struct, it could be an array of struct, it could be a function, whatever, then there are certain attributes which are naturally associated with this declaration. Okay, so I'll have a follow-up slide which I'll explain it in more detail. But it says that if you have a name You are given a name, so the name of course is associated or introduced by the programmer. The data type is also given along with the declaration, so that is obvious, it's an attribute. One attribute of a name is the type, int, struct, array of struct, whatever. Once you introduce a new type name, or you create an object of a certain data type, a size is implicit, which is decided by the language designer, the architect and so on, but it is fixed. So the number of bytes which this data type value will occupy is decided, and is yet another attribute. Another important attribute which we call is the R value. R value is the value of that particular entity. I'll give an example in a very short while. There are many more important attributes. One of the attributes is called scope. So in C, the scope rules may not be very complex, but still there is something called scope which you probably know. Whatever I need to introduce, I will in a short while. And a very important attribute of a variable or entity that you define is called lifetime. Much of these have some implication with the errors that come with pointers, so I'll take them up in the right point in time. And I'll give you some more examples. So the next line says variables must be assigned memory locations. Anything whose value is changing in the program, you cannot not give it a place to stay, which is a memory. However, constants, a string constant, character constant, a float constant, an integer constant, does not need a space because it can be directly manipulated as given. Architectures have instructions in which you can directly use these constants, so they are not given space. That you should remember, because many errors come because of this particular. The one which I am looking at really interested is the last one, which is called memory location. So memory location is assigned to every object or variable that you introduce in the program, and we will like to call in this course this as a L value as compared to R value, and I'm going to explain that on my sheets in a very short. While I do it for exactly one declaration, make sure it's a very generic statement and it holds for everything that you can introduce. So I'm going to introduce a very simple thing. I'll put something called int I equals say 10. This C, so I'll put the semicolon. Even an innocent declaration like this, what have we done? We have defined a name which is I and some attributes of this name. So I'll draw a box. Whenever in doubt, you can do this box, what I'm doing. The box is the place in which I will stay. Now let's write the attributes. The name of this box given by the user is I. Actually is given a name I, the box is given by the system. A value 10 has been put. 10 is the R value attribute of I. So R value is 10. The type attribute, since you have defined, is int, so we'll note down the type of this entity is int, is all attributes of I. Space, okay, or the size, I'm assuming int is 4 bytes, so this is 4 bytes is assumed. Now you can go into the other attributes. Where is it defined? Is it outside the main or is it inside the main? So maybe it's a global variable, I don't know, we have to figure out. Maybe it's a local variable. Maybe it's a static variable. There may be other properties which I'm skipping for the moment because I don't see any of them. And I'll come to the last important attribute for me, which is an L value. If a box has been created in memory, it has a unique address, and that's the L value. Okay, so minus some details, these are the attributes. So whatever I've given here are the basic attributes which are all inferred or deduced from the declaration, the result of the declaration. So the point is, whether pointers are there in a programming language or not, it does not matter. All programming languages will have to assign this address. You'll have to give a piece of memory to hold a value. And therefore implicitly a pointer is always there in all programming languages which use variables. So without memory, you cannot operate on that particular entity. See, if addresses are assigned, I think the languages which came after Fortran said, why not make it a first-class citizen? Which means, why not make a pointer as an independent data type. Just like int is a data type and so many others are data types, a pointer can also create a data type of its own. Or we can deal with the world of addresses for whatever purpose you can make of it. If you are giving somebody an address, let's make that address known to the programmer. And that's how the world of pointers got introduced from a language called Pascal onwards way back in the 70s. So in C, pointers are well established and we are going to enter slowly. So pointers and addresses for most part of my course will be synonymous. They mean the same. So now going back to my slide. Okay, so whenever I say L value, I imply or I mean the address at which an object is or an entity is stored. This is exactly what I said a short while back. The last point is the motivation for allowing pointers to be first-class citizens in languages or to allow the programmer to use or access the world of access of the address. Okay, so let's move on. Now if space is allocated, somebody should know how you allocate space. I don't think I'll have to say too much over here. This allocation of space is decided by the language designer. So C has already said how many units of memory to be given typically to different values of different data types. So the last bullet says if you declare an array A of size 100 of type short, then on most architectures, then short takes 2 bytes, 200 bytes of consecutive memory will be allocated and the start address will be the address of A0. This will be known to the system and therefore if you are allowing pointers as first-class citizens, then somebody, a programmer, can also figure out what is the address of A0. Here is a concrete example from C. I'll take a lot of examples. First, a small caution about the examples. The examples that I run or we at IIT, most IITs, use only open source systems. So we'll work on, all my illustrations will be on Linux operating system and use of the GCC compiler. So this combination is where my experiments or my examples relate to. Okay, we know that there are many other operating systems including Windows and there are many other compilers in the business. Generally, if one is looking at a C compiler, by and large it should not matter, okay, what is the operating platform. Which means the compiler, OS and things like that. But however, that is idealistic. It so happens that depending on which combination you are using, there may be minor differences. For example, the number of bytes assigned to a particular data type may be architecture dependent. So therefore, these examples you should take in a generic spirit. If there are variations on your system, the explanations that I give should be roughly the same. Okay, so let's look at this. I have defined an int I, a car ch, an array of float of 20 values, assigned short, not unsigned, but assigned short for whatever it means, and then a double. And what I have done, I have actually written something which I'm sure all of you know, to find out what are the addresses assigned by the compiler at runtime to these entities. So I'll tell you, if you are not familiar, I'll just spend a minute or two trying to explain how to read this data. Okay, so observe that most of this data, all address data always is prefixed with 0x, which stands for hexadecimal base 16. While this may not be very comfortable to the humans, it's very comfortable to the machine by virtue of how it has been built. Okay, so 0x stands for hexadecimal and whatever you see after that is a physical memory address in base 16. Okay, but you observe that most of the leading digits are same. Okay, for example, if you look at anything except the last 2 digits, everything is some CC and starting with a CC. So let me ignore all the digits except the last 2 and look at them. So I'm going to write over here. The least one that you can see is 91, which has been assigned last 2 digits to the data type CH. Okay. The next is 92, which is assigned to SS. After 92, looks like 94 is assigned to I. And then you have 98, which is assigned to DD. And going in ascending order, increasing memory address. And the one which is looking funny, this A0, I'm going to explain in a minute, is assigned to X. Observe that this is not the order in which the declarations were defined. He has given the least address to CH, whereas I had defined I as my first address. So it does not matter which order you do, because address is not really dependent on us. When you go to a hotel, you may say, I want room number 5, but you may or may not get it. You'll get some room, all right. Similarly, the rooms are not important. The order in which they're given is not important. But whenever you refer to I, he will look at this particular address and so on. What has the compiler done? How is the memory address done? So observe that typically a car in C is 1 byte. So this byte number 91, okay, let me draw it elsewhere. If I draw the memory in a long chain fashion, I write the addresses below, each is a byte. So 91 is where the CH value, the value of the character has been stored. The very next address 92, observe, is SS. The next one 93, nothing is mentioned, but 94 he says is the address of I. So since SS is 2 bytes long, you can see that it occupies 92 and 93 is a short. Since I is 4 bytes long, you can see therefore 95, 96 and 97, all of these are occupied by I. There is no wonder that 98 therefore is a start of DD. Okay, so this is where DD starts. How long is DD? I have told you that on my machine DD is 8. So if I take 98 and add 8 to it, since I have to do hexadecimal arithmetic, I'll do hexadecimal. When I add 8 and 8, 16, in base 16 this is 0. And 9 plus 1 is 10, but 10 you cannot write, so 10 is same as A. If you are comfortable with these digits, 10 is A, 11 is B, and so on, and 15 is F. The hexadecimal arithmetic spells itself out. So 98 plus 8 is A0, and therefore is no wonder that A0 is the starting address of the float value, which is, okay. So in other words, you don't have to do it, but if you are in trouble, and you are finding it's a very hard to discover error, go a step behind, look at these addresses and see if there is anything wrong with the addresses which are assigned to memory. Are you doing something wrong in the way the addresses should have been? So you can look at the addresses and figure out how the system has laid out the different units in memory. Typically not required, but only in times of trouble it may actually be a life-saving opportunity. Okay, so you should be now familiar with hexadecimal, familiar with the fact that addresses can be actually seen at runtime while your program is running. It should also be clear that these are not reproducible. If I run the same program again, I will not get these addresses. I will get some other address. Similarly, just like if you go to a hotel again and again, you are not assured of the same room. You will get a room of the same type and class that you pay. Similarly, the addresses are not necessarily bound to be same. Actually, they are not same often, but they will be relative some addresses. So for that run, these addresses are. For example, in this particular declaration, a struct student has been defined. If you do my quick calculation here, the first data is an integer 4 bytes, followed by gender is 1 byte 5, 100 character array is 100 bytes 105, short is 207. So the requirement is that one value of type student requires 107 bytes. But typically the systems do not want to give you an arbitrary number. They love to give you units of multiples of 4. So he has decided to give 108 bytes, 1 byte more than what is the requirement. Such gaps you will see. Usually they do not cause a trouble, but sometimes they may, because there is an extra byte hanging on to your data which really does not belong to your data. Now you may not know where is that extra byte. Is it after role, after gender, car, after the name, after age, before age? That is sort of unpredictable. But the system knows what to do when you refer to these names, when you refer to your fields. Okay? So here I have taken the same old example. I will not work it out for you, but you can see now. If you go back, What is ABC? ABC is supposed to be an object which will be defined of type student. So right on the beginning I have said struct student ABC. Compiler allocated 108 bytes. If you want to look at any of its addresses, the address of the type student or of the type ABC is the start address, the first address, which is some F0 in this notation, last 2 digits. Okay, so this also shows you something like this. So for a struct, as you can see, I'm just looking at addresses right now. ABC is the name of a student data. The typical fields are, one is called role, other is called gender. They are the names given by me. Then this followed by a name array and so on, and followed by age. They have different types. Okay. So when you just say ABC, okay, you can get the address of ABC by looking at where this whole thing started. So this is the address of ABC. Now observe, the address of ABC is also exactly same as the address of role, because they are the same things. But the address of gender is so many bytes away from the address of role, which depends on the number of bytes given to role. If role is an integer, then gender could be the address plus 4 and so on. So here it shows on the slide that all these addresses can be obtained by a person or the programmer if he or she wishes. Now let's go to a higher level object. We looked at arrays, we said all addresses can be figured out. We looked at structs, we said all addresses we can figure out of even a composite value, or for any values of different types, all addresses can be figured out. Because they are assigned by the compiler, even at runtime, a programmer can see what those addresses are. The slide which is up there now talks about addresses of functions. So what are functions and what does it mean to say there is an address of a function? I'm again talking about memory. So you see on the second bullet, we have 3 different functions. One is an add function. It has some specification I'll ignore. Another is a mult function. It also has a specification. These are all complete definitions. And there's a main which does not have a parameter, does not have a body, it's just out there. Even with these 3 definitions, if the user said, I want to know where is main, what is the address of main, this is a legal question. The system is bound to answer you, and it answers. It says it is in the hexadecimal address 4,553. Address of add is something else, and address of mult is something else. So I hope you are aware that this is a very valid observation. Okay? If your mental picture of a function is right, then you would know that when you define a function, let's say add, or you define a function mult, which I had done, or you define a function, I'm drawing these circles just to show that these are some functions, okay, these are all functions. What do you mean by address? So these source functions are translated into code, right? Target code, object code. The compiler converts each of them into object code. Is generated for each function. I'll open this model much more clearer as we go along. So address is put somewhere in memory. So one is saying if you're asking for an address, is the start byte at which these have been kept. They are all in memory. So this is the address of main, this is the address of mult, and so on. So each function is compiled, is placed into memory. There is a starting byte from which the function has been laid out. We have not told you what is laid out as a part of the function. And therefore it is legal to ask what the address of any function that you have defined. Now can you ask for a function the address of a library function? I leave it for you to see. But all functions defined by you, definitely you can ask because they have been assigned memory. Okay, so now I'm coming out to, there is no linked list, there is no runtime data yet. I still don't want to enter there unless I'm very clear that you are comfortable with basic data types, derived data types, and taking addresses and working with them. Okay, so the first use of this operator ampersand, again I assume you know, ampersand followed by any object. You must have created an object, you must have created a variable, gives you the address of that variable. So look at this print statement. I've quite almost forgotten about printf, working with C++ most of the time. But anyway, so there is %d which will print an integer value, which is what corresponds to the argument I. I is printed using %d. Then ampersand I is an address, and therefore it's printed using %p. If you know this, great. So then you will be getting, as a result of this, an integer value and an address. The point is, why could I get the address of I? Because I have introduced int I equals 10. I have created variable I, and I have full right to find out what is its address for a given runtime, a particular time when you are running. If you can do it with I, the point is you can do it with anything that you have created. So in this slide, I have created the same struct student, and you can look at these prints. The way I generated the addresses I showed is this. Here is address of ABC, which is ampersand ABC. If you want address of role in the C syntax, you have to say ABC, the name of the variable, and then dot the field. So, and abc.role gives you the address of role, and so on. So the address of any member of a struct can be easily figured out. Address of an array can be figured out. Address of any data type can be figured out. So since I can ask addresses of normal objects, can I also ask addresses of functions? The answer is yes. You observe, same function that I have written, and I have come over here and I have said printf address main, address add, address mult, and all of this will be responded to by the compiler, the runtime environment, the OS showing you what is the address for a given execute. So the address operator is very powerful, and for every object that I create, I can ask its address. Later on, I'll extend it to even the pointer data type. So every object created by us in a program which is addressable, which means not a constant, you can't do it for a constant, you can always ask an address. And okay, so let me ask you a question here. It's a question that we ask often my own students. It's typical of C++. So if I wrote, for example, ++++I, okay, and just left it like this, is this an error or not an error? Let me first get your answers. And if it's an error, what sort of error it is? So if you want to answer me, talk. So these questions I'll take up later on, but anyone wants to answer? I have 4 pluses followed by an I. What does happen and why does it happen? More important is why does it happen? Anyone wants to have an answer? Okay, I have seen these questions. I'll answer you in a short while. Enumerator, data type, and others. Illegal use of the operator. Why is that? Why do you think it's an illegal use of an operator? What you said is very close to correct. It's actually correct. But why is it? So one of your person, Gajanan, said it's an illegal use of operator. Which operator? I presume ++. And remember, this always may not be. For int I, it's an error. So let me give you a quick answer and then I'll move along. So it goes like this. This operator or this expression is broken up into an application of ++ on ++ I. Now ++ I, as you know, if you have some value of I, whatever that be, say the value is 6, ++ I adds 1 to it and therefore returns the value 7. Okay. So this will be further, this will lead to applying ++ to 7. Now ++ is an operator which is only allowed over entities which have memory. It must have an L value. Now since 7 is an R value, does not have an L value, this is failed. So the point is that this ++ I returns a constant. Even though I is a memory, ++ I is a constant. And you cannot do a ++ on a constant. So you have to always remember the difference between L value and R values. So if for some particular operation, if ++ I returns a value which is having an L value, if I do ++ P, for example, where P is a pointer, okay, then what it returns, if it turns out to be a pointer again, then you can do a ++. So it's a little complex, but yes, the point is to figure out a ++ operator is only applied to an entity which has a memory and a constant does not have memory. That's the real reason, therefore it's illegal. So essentially you have to remember all these small differences which can come up by understanding the language rule very well. So coming back to the slides. So somebody said I value is incremented twice. That is not correct. You can increment I value twice, but you cannot increment a constant through ++. So now coming back to the pointer data type, the pointer data type basically are objects that are typically obtained after doing an ampersand operator on an object. You return an address, and if you want to work with addresses, then only you get into pointer data type. I said a data type must have a value space, a set of values, and it must have operations. So the values of a pointer data type are addresses. So therefore, if you have a 1 terabyte RAM, then byte 0 to the last byte are all values of your pointer data type, and the operations we'll see in a short while. It has very few limited operations because you don't want to deal with operators like general data. So this language C permits only a few restricted operators, and then the entire data type is defined. So all addresses which are genuinely produced in your computer are values of the pointer data type, and the operators, which are very few, if applied, completely specify the data. So I'm assuming you are familiar with this thing called T star. Okay, this is how you define a pointer. A few examples so that I can move a little faster. So you can write int I equals 10. Then you can write int star p int equals ampersand I. Now look at the second statement. That's the one which is important for me. So maybe I'll do it here. I have a few more which I will do so that you don't get confused in reading pointers. Okay, you can write anything and then check out. What I have written here, I'll borrow the same thing. I have an int star, I have written p int, and I have written equal to ampersand I. And it was before this, we had already defined int I equals 10. This was defined before this. So when you read this particular statement, if you're new to pointers, you should do a little carefully. This is the declaration on the LHS of equal to. It defines p int is the name given, is of type pointer to integer. You should always read like this. So if this is the declaration of p int, whatever follows before this is basically its type. Anything. So the type of p int is, if you read from right to left, star stands for a pointer, pointer to int. If I wrote, for example, int star 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 p and then stopped here, I can read this entire declaration in different ways. If I want to know what is PPP is a pointer to, which itself is a pointer to, which itself is a pointer to an integer. You can see how complex it looks, and therefore is the cause of most trouble. So what is PPP? Somebody asks. I have to go slowly. I have to first create an integer object. Okay, here's an integer object. Then I create an object which is a pointer in which I put the address of this integer. So if it is 1000, I put 1000 here. Type of this box is int. Type of this box, since it has an address of the int, this is int star. It is a pointer to one integer. So suppose this is put in 2000. The address of this is 2000. I put this 2000 deliberately here so that this fellow is pointing to this particular element. So now since this is already int star and this fellow is a pointer to int star, he becomes int double star. But everything has a memory. 3000 may be placed in memory location 5000. If I take some place and put 5000 here, then what have I done? I have taken an int star star and put a pointer to it. So this whatever put over here is basically int triple star. And this I have said is PPP. So PPP will look something like this. Don't worry about it. It looks horrendously complex only for testing purposes. You don't really use too many stars. But if you have to use, then there's a very clean way of decoding this whole thing. The name followed by read from right to left and read every star as a point. The whole thing will become somewhat clearer than what it is. So the point is, when you create an address or when you create a pointer, then you must assign something to it. It's good to assign something to it. So this, observe this now. This is a very compatible and correct assignment in which we have said int star p int. I could have just stopped here. This is also a valid declaration. It says I have something called p int. It has a value which happens to be an address of an integer object. That's all it says. But there is no value anywhere. So a correct thing to initialize this will be what we did over there. When we did something like this, address of I is address of operator. I was already defined, so there was an I which was having a value 10. Maybe it has an address 1500. Now this assignment now says in pint put the value 1500. So I put this value 1500, because of which this now points to this particular place. I have a slide very soon coming up where we'll tell how to look at such expressions and figure out whether they have an error or not. Often you can create errors over here. The errors or not in such declarations, in such assignments. Okay, and I'll do it along with you just like a compiler does, so that it will become clear. This is the first starting point where I'm introducing pointers. So what have we done? We've introduced a pointer variable using the pointer data type *end, and I've also assigned. I don't know what to do with it, but at least I can introduce, because a data type called pointers have been allowed in the line. Okay, so this is what I did in a short while back. I'll use this slide only. So this says if you introduce int *pint equals &I, and I happens to be 10, then what are the various names that are coming up over here? So what is type of pint? It is int *. This is what I said. If you take a particular name, look everything to the left of it, and read it from right to left, and that's what its type is. So pint is pointer to int. What is the type of *pint if somebody says? So what I do, I take *pint, put it on the right side and see what is to its left. The first line declaration says to the left of *pint is only int. So this says now the type of *pint is int. Read the last line over there. It says star followed by a pointer. If you use, then it is called dereferencing the pointer. You are saying, I don't want the pointer, I don't want the address. Please take the address, reach out to the object which is placed in that address and give it to them. So while P gives you the address, *P gives you the object which is placed. This operation is called dereference. So others are here. I hope you are comfortable with them. Otherwise, please write programs and make sure that you get comfortable with them. So here is a slide in which I have done things very properly. Okay, I may not do always, we not always do things very properly. What do I mean by that? I'll take one or two lines. The first line declares or defines int and I as an integer. And if you come to the fifth line, there I've defined pint as a pointer to integer, and to this pointer I've assigned the address of I, so it holds the address of I. So I have declared a pointer of integer and I put an address of integer. This goes very nice. There's no issue over here. Similarly, I have defined various things. I have defined, for example, float x20. Okay. So there's a float array of x with 20 values. And now see at the end, I have written here float *p float equals no ampersand, just x. Okay, this looks confusing. So again, look at it carefully. Just look at float x20 and look at this declaration or definition which says float *p float equals x. So let's read the left hand side. Left hand side of the equality is p float, and to the left of it pointer to float. So it's clear, it holds the address of a float. Now we have assigned is x. Now what is x? X is an array. But I've told you whenever you use an array in C, remember it is same as the address of the first element. So x is same as address of x0, and therefore this assignment goes. Name of the array is the address of the first element. Address of an element is also a pointer to the element. So the left hand side is float *, right hand side is float *. Valid assignment. So typically what you do when you create a pointer or an address of an object, you assigned it with the address actually of an object that you have created. Then there is no issue. Okay, now these are tricky problems and look at it carefully. This I'm trying to give you some mix of issues when you deal with pointers and arrays. There are many issues, but this is one of the basic problems that you deal. So observe, if you just used an array and ignored pointers, you don't like pointers, and this is how you will do in the the upper part of the slide. I introduce a of 1000, then I write a loop. In that loop I assigned ai some value. I've done I square, which is fine. So every value of the array is assigned. And in the next for loop, I am asking him to print out the values which have been put into that array. There's no pointer there, looks very fine, typically should not give you a problem unless there are some other issues. So look at C way of rewriting the same code using only pointers and completely ignoring the array notation. If things are going fine, you will get identical result out of this. What have I done? I have declared an int star, an address of integer, a pointer to an integer, and I have made it equal to a. Where have I put it? After declaring int a1000. So P has the address of a0. Now probably I should do it here. I don't know how comfortable you are with pointers and this. So I have this funny statement out there in the first for loop which says star P plus plus equals I star I, and then it says P plus plus. This should not have been there, but it doesn't matter. Okay, this is a part of the loop. How do you decode this? What is P? P is int star. Type of P is int star. It's an integer pointer. So how do you decode this expression star P plus plus, and why? So it cannot be decoded according to my wish or your wish. We have to follow the rules of C language. Without wasting or deliberating too much on this, the language has defined the set of all operators. I have it on my slide somewhere, which you can read up. The operators are precedences, and in this the precedence given as plus plus is a higher precedence operator relatively as compared to star. Very deterministic things will happen. So the star P plus plus will say please do it in this order, but P plus plus says first use P and then increment. So this amounts to please dereference P, okay, and then do P plus plus. What does it mean in this case? What is P? We had assigned P to the start address of my array. If this is a0 address, then P is basically here. This is the pointer to the first element of the array. And what is the statement saying? Star P plus plus equal I star I. It says please dereference P. So take the current value of, so we go to a0. And what do you put there? Equals I star. So 0 star 0 will come here. And after that, that P will automatically move because you will do P plus plus to the next element of the array. You'll put 1 square, 2 square, whatever. And this array will build up without any array notation because I am hanging on to the pointer and moving through the array. This is very often done in C code. Not advisable. I would always prefer to write the code which is on the top. However, on many reasons which is beyond the scope of this course, it turns out that pointers are more efficient and quick to implement as compared to an array. But the point here is that an array can be accessed through a pointer to the first element in a completely different manner by just doing pointer arithmetic. And you can see some instance of pointer arithmetic have already been completed. Now if this is clear to you, there is a very funny statement sitting in the middle which is P equals A. And I have a question for you. You have to tell me why is this P equal to A there, and if I drop P equal to A, what might happen? Not guaranteed, but what might happen? Okay, I can see some questions. I'll take up questions maybe a little later. Let me complete a little more. I have noted everything. Okay, so I have something. So can somebody answer the question that I have asked? If you can see the slide, there is an innocent statement, almost useless statement, which puts P equals A. And I'm asking what might go wrong if I replace or remove that P equals A and do the rest of the code. So my statement was, if you keep the two sets of codes identical as I have given, it will give you the same result. You can try it on your system at leisure. But if you drop that P equal to A, depending on how much memory and what your configuration is, you might see something interesting happening. What is that? You have to guess. You should not run and see. You can of course run and check, but then that's sort of defeating the purpose. Because often when you write some code for the first time, you don't know what is happening. Okay, so I have more on that. I'll not take too much more of your time. So let's go back. I'll try and explain why that P equals to A is important. So if you observe, what I did is, so assume this was the array size is not important. Suppose I had a size of array from 0 to 10 or whatever, 0 to 9. Okay, this is my array A. What was I doing? I was using, instead of the array notation, I used a P and in P I put the starting address of the A0 by some means, P equal to A or whatever. So P was same as address of A0 that I had initialized. This was done. And then what did we do? Then we use this P to populate. So I put 0 square here, then I put 1 square here in 1, in 2 I put 4, and I went ahead and put in 981 if things were done properly. Where is P at the end of all of this? When I've completely traversed through, my P is basically somewhere starting around here, give or take a byte, because P has moved, continuously placing in the array location of that. If I do not do P equals, say, after that what did I want? I wanted to display these values. So if you want to display the A of 0, then I have to go back and set P back to A. Okay, so if I do that, then my P after this is knocked off, resumes from here, and then I can walk down and give you all the values. If you drop P equal to A, and similar things happen in many real programs, the scenario that is happening now is, reclaim this. So here is my start address 0, my last array 9, and P currently is here. If I don't bring P back to this, P will be used to continuously view the elements of the array. So P will go and access this, and it will assume and keep accessing these elements, 10 more elements over here. So P will go beyond the array access. And depending on how lucky or unlucky you are, when you go beyond your assigned space, you often get this strange fault which is known as segmentation fault. Which is a runtime error, and your program will get abnormally terminated and will be thrown out of by the operating system. Typically, if you have encountered segmentation fault before, you would know that often, if not always, a pointer is behind this problem. Right? So typically, as they say, if there is a fire, it will give you smoke, or the other way around. If there is a smoke, there must be underneath a fire. Similarly, if you see a segmentation fault, 90% chances are that you have misbehaved, your program has misbehaved with respect to a pointer. And the misbehavior here was, I'll talk about it later. One of the major problems with pointers are, if you are not careful, you will get mercilessly thrown out, because we try to peep into somebody else's window, some other memory space which does not belong to the program which is existing. Okay, so this I am going to skip. This is a similar way in which you can take a pointer of an object created through a structure, my data type, and then I am hoping that you know the syntax. You take a pointer, use an arrow. The arrow notation allows you to run down the different components of the data type that you have defined. The last line says P student arrow role. If P stud is a pointer to a structure object, this is how you get to its role field. Whereas if you have an object by name like ABC, then you use the dot notation. This C, so I'll assume that you know that pointers can be created to structure elements also, and you can access it just like you can access an array. Here comes in, somebody had asked a question about pointer to main. So look at this. Okay, so you can define pointers to functions also. Okay, pointers to functions, why do we define? Maybe we can ask first the question, why do I need a pointer to a function? As such, pointers are so complex, functions are not at all simple. Why does one want to have a combination of these two? Well, I want to have a pointer to a function itself. So if you have done C, C++ and other languages, you would know that pointer to a function is a very vital piece of flexibility which is given to a program. But before that, let me cover this slide. This slide says, I'm assuming you are familiar with type def. Okay. What does the first type def do? Can somebody tell me? What is the first type def, or all these three type defs? What are they trying to do in my slide over here? What is the purpose? Okay. So what is type def used? Okay, I will not waste time. I'm sure many of you know, some of you might have forgotten. So type def is a way in which you can use some shortcuts in C. So you already define a type, give it a short name, and then you can continue with it. So for example, if you look at my the first type def that I given, I'll write it out here so that you can see. and then the rest should follow. It's a very powerful feature if you don't have advanced features of C++. Then this is quite useful and many of us do use it in a different form. So let's take this and try and explain. This is one. You can also take the second one. It's just a convenient vehicle for a person, for a program writer to do something much easily. So observe the syntax. The syntax is always type def. Before I go to the function definition, you take an actual type which is already defined. So take any type name or define a new type and give it a name that you want to use, name which you choose. So for example, look at the second one. I have defined a structure here, but I don't want to write this every time. So I am going to use this name str whenever I want to do this. So after I have done this type def, I can write str whatever I want, object 1, object 2 or structure 1, structure 2, and that's enough. I don't have to write this long string over there. So a complete structure definition has been abbreviated or renamed to a simple name that I want, which is easy. It's quite easy to understand. Only problem is, what is this function definition do? So first we have to understand, typically functions have a return type. In this case, this function has an int return type. Okay. The function name is not known and it has two parameters which are both integer. This is the function notation in C. Typically it should have a name. So function has a name, it has a return type, and it has some arguments optional you may or may not have that you need to pass. These are the formal arguments. What do we want? We don't want all of this. We say, okay, there is a function, all right, but I don't want it. I want a pointer to this. So knowing that this function will be stored somewhere in memory, I just want the starting address. Okay, how do I define that? So now look at this definition. This definition, this pair of parentheses is very interesting. This basically stands for a function, because functions usually have arguments. So you read it like this. Ignore this for the moment. So this notation is a function. So this notation says, I have a pointer to a function. Ignore this name for the moment. So this says pointer to, this notation is a function which takes two integer arguments, has a return type int, and the type def says this kind of functions I will use the name fptr. Okay? So look at this complex but cryptic notation. This is the type def name. So whenever I want to point to a function which has a return type int and two arguments, this fptr will be pointed to such a function. Now if this is clear, then I can read the next of your slide and see whatever I am saying. So the first one says fptr is a function, is a pointer to a function which has that characteristic. The second one says there is something called a main ptr, name is main ptr by type def, which is also pointed to a function which returns int but does not take an argument. Okay, and now look at two concrete functions defined, int add and int mult. Observe that add and mult are both agreeing to what we have tried to declare through a fptr. Fptr basically is a pointer to function with two integer arguments and one return argument. Both add and mult agree to this kind of a function definition. Okay. So coming back to this small program fragment, pointers to functions, you observe what is being attempted over here. Right now it is hypothetical, so don't bother. So there is a structure which we are trying to define, which has two entities. One is an integer value and the other one is a function pointer defined as a point. Okay, so this structure had two things, an integer and a pointer. So when I get into the program, I can do these funny things. I can create an object. Okay, that object name, actual name is object, which is of type str, and then its arith op field, which is a function pointer, I've assigned to add. Observe, there is no address. Since it's a pointer and the name add is itself a pointer to the function, this just goes through. So I have used a function pointer to assign to a field of a particular object. And the next one, observe, is even more interesting. It takes this field, it dereferences this pointer, essentially calls the function add with arguments 11 and 13. So coming back to my statement, where are function pointers useful? Function pointers minimally are useful where a person wants to apply different functions at different scenarios. So suppose I have a function, other arguments, and I write a function like this. So since there is a function pointer, depending on my need, I may use function f1 and call it, or I can sometimes call function f2, or I can call function f3. So I can control at the call side by giving different function pointers, which are all of agreeing type. They should have the same return type, they should have the same argument type, and so on. So if I can write a function with a function pointer, then I can use it to call different functions depending on my need. So for example, if I'm looking at different search functions, depending on my data structure, I can sometimes call linear search, I may call binary search, because these are by pointers, and make sure that any of them are. So I can even in instance change the body of my function depending on what I want to do from outside. If you are familiar with virtual functions, which is much more complex than what I have given, the basic element of translation is in having some sort of function pointers. So function pointers are useful even to programmers. And this shows that if you are writing such code, this compiler or the C system has given you full command over knowing where that function is, assigning it to relevant things, and you can call functions using this function pointer. Okay, let me resume now. So I have given you the basics. Okay, I've taken you through the two operators which are fundamental. If you look at a nutshell, there aren't too many things which are involved in this data type in C. You have an ampersand operator, you get an address, and you have a star operator, dereferencer. That's about it all. But when combined with other data types, it can give you very powerful mechanism to implement very many different data structures, as we will see in the next. So this is a very short table which tells you what pointers type, where pointer types can be used, and what operators are defined. You observe that there are very few operators which are defined. I'll not get into the syntax and semantics. So if you look at the last ones, you can assign pointers. Okay, you can do some addition of them. You can compare two pointers. You can compare for equality, inequality, or that is more often, that relational is really not typically used. You can do minimal addition and subtraction, but no other arithmetic. You can dereference, and you can take address. You can do unary, plus plus, and minus minus. And of course, if you have an array of pointers, then you can use the pointer. So very few operators are allowed, and even then some of these can give you problems. These are very simple, some 7 assignment statements are here. Okay, and I have put some question mark against these as comment. Int I equals 0 is unquestionably correct in any implementation of C. Okay, and I would like you to check and see. I'm going to help you all do that, to figure out how different languages will look at it. And let me assure you that C and C++ do not agree on many of the issues, many of the errors that they may issue out of it. So let's intuitively do this, and you can run subsequently and verify as to what we said is actually done on it. This is to make sure when you write things involving pointers, have you done this mental exercise, which I would do. I'll ask you to do whenever you use pointers. Okay, don't be in a hurry, take your time and do this. So is this, I'll do for each one of them. Int I equals 0. What does the compiler typically do? It observes that you have defined an entity called I, whose type is integer. Now it checks whether the RHS and LHS are compatible. What is 0? 0 typically could be of type int, could be of type short, long also. So he says, okay, an int is assigned an int, please go ahead, do whatever machine language code you want to generate. This is passed as okay by the compiler. Okay, so the language basically says this is acceptable, you are doing fine. Integer object, assign an integer value. What is the next one? Let's do it for each one of them so that you get accustomed to working like this. So I look at the left hand side. What is being defined? IP. What is the type of IP? Int star, pointer to integer. RHS. What is I? Int. When you take an address of int, what do you produce? You actually point at produce a pointer to integer. Okay, no issues. Fast. Right? Now let's look at the third one. Int k equals ip. What is k? What is the type of the left hand side? Int. What are you assigning it to? IP. But IP is done above. What is IP? Int star. Here there is some kind of a mismatch being done. A pointer is being assigned to an integer. Now, depending on how strict or loose the language is, he may throw you out, but there is some inconsistency here, because the RHS and the LHS are not compatible on types. Okay, the two sides are not compatible. You can check what C says. If you have more time, you can check what C++ says. Why am I saying this? Because often I think I have one example which I would like to do today, that I can show you the differences between the two compilers. One passes, the other. Similarly, look at the next one. So I have unsigned int star. Yeah, I'll not do all of them. Maybe it's the last one I'll do. But you should be able to do all of these using the same style that I am doing. UIP equals IP. What I am supposed to do? Find the type of the left hand side. Type of what? UIP. The type of UIP is unsigned int star. Read in English, a pointer to an unsigned integer. Okay. These integers should not have sign. They are only greater than equal 0. What is IP? Defined above. This is int star. Okay. So again there is a problem. Though they belong to the same family, but they are not really the same. This is a pointer to an integer. This integer could be signed or unsigned both, but the left hand side says I want only unsigned integers. So again there is incompatibility. Okay, they are not compatible. And if they are not compatible, something strange may happen if you force this through. Okay, so I am not doing the rest, but you can check out now that some of the remaining ones will go through and some of them will not go through once you look at it carefully. For example, look at the last one, the last assignment. IP4 is the name of the variable, which is of type pointer to integer or int star, is assigned a value I whose type is int. So this is illegal. Typically the compiler will throw you out. Even if it does not throw you out, it may give rise to disastrous results. So since I find a lot of questions, I would like to take them up. I'll just take one more slide and then I'll return back to the questions. This I've done covered anyway. Okay, so I don't have it here. I have it in another version. Okay, so I'll take your questions. But before that, let me tell you. So let me take the questions now. I'll probably try and see wherever, maybe take the questions from the first come first serve basis. Okay, so this is the first question. Our sir has told that int has only 2 bytes, but you are saying it has 4 bytes. Which we have to follow? Good question. See, the question, the whole issue is about which system you are working. Don't believe in sir or don't believe in me. You have to believe in yourself. How do you do it? So this is what you should do. Don't trust any one of us, because both of them are prevalent on smaller architectures. Machines which have low, memory and whose instructions are of the older kind, they will typically use 2 bytes. Most architectures of today, Pentium and onwards, do not use 2 bytes. But it is not to be worried. So what you should do is, on any machine that you work, you should be able to write, just do this size of int, okay, and ask them to print it. So do a printf of this. Size of any type is a built-in function. If this returns 2, you accept 2 for your machine, that is God. If he says 4, accept 4. If he says anything else, accept. So what you have to do is, because these are variable parameters, right? So to say that if you take a double bedroom in a hotel, it will have exactly this specification is very difficult to say. It may have something more or less. So typically both go. Most open source machines and most recent systems will give you 4 bytes for an integer, not guaranteed. May give you 8 bytes for a long, okay, and may give you 12 bytes for a long, but these are not guaranteed. What does the language guarantee? The language guarantees that short is less than equals int is less than equals long in size, and long is less than long. But most common things that I have found are, this may be 4 also, it depends, but this is typically 8 or 12. So my answer is, don't take anybody for granted. Write a 2-line program, ask printf. If you want, I can write the program for you. This is the program. If you don't, or you're not comfortable doing it, of course put stdio.h and so on, and you don't have to do anything, no declaration, just write printf code. Now this, I think size of is typically unsigned long, so you have to give that, or long unsigned, %10 or something like this, and what I said, size of it. So do something like this, correct the syntax if I've done anything mistake, and this is your program. Look at the answer and decide which is correct. Okay? You change machines, you will find different things correct. Okay, so this is somewhat machine dependent. Architecture dependent is a more correct thing, and therefore the compiler does what the architecture allows. Okay, so this is one question I saw. Then, is the null pointer same as an uninitialized pointer? This is, you are relying on the goodness of the compiler. Please don't. The compiler is not honored to do good things, right? If you leave your wallet in a bus, if somebody returns to you, you should be happy, but you can't demand that, isn't it? So typically, if you put any pointer, let me take int star p and do this, and then if I say printf, I'm not very comfortable with C, so if there are mistakes, please correct it yourself. Okay, so I want to dereference. Okay, so percentage, I'll not put this. I'll put %f, %d. Okay, and I'll ask both. I'll say give me p is the address which will give you, and then I'll say star p. This is all that I've done. So what have I done in my box style? I've defined a p. P will definitely have an address. Maybe it is addable to 2000. What is in here? I don't know. Everything has a bits 10. Something is in here. Okay, whatever the machine had before you started, some bit pattern 0 and 1 is here. This is what the scenario out of the declaration is. So when I say print p, okay, he's trying to put out the address. So this he will take as an address, okay, which may be fine. So if it is having some number, it will give you maybe 3000, whatever. So whatever is stored in here, it will say this is the address. But once you say star p, then it has to go to this address and decode what is the value in here. And this is the point where you will get most likely a segmentation fault. Right? If you have made a payment, you bought something, you want to make a payment, you must make the payment from your wallet, right? Not somebody else's wallet. So what we are doing here is this number, which is unfortunately 3000, I am saying go tell me what is at 3000. The system is not obliged to tell you what is in 3000 unless 3000 is in your area, which is very, very rare. Probability of a random pattern accessing a memory outside your area is very, very high, looking at the enormity of the area. So most often this will give you a fault. And the reason is, which your friend correctly said, this is a very wrong thing to do. Some compilers who are good, seeing it's a pointer, might put the null pointer or 0, but you can't guarantee on that. So correct thing will be, if you really want, you should put int star p equals null or 0, and then you have actually done what you want. Let me take the next question. I don't know where the questions are vanishing. In this case, star p plus plus, so data need to be stored in alternate memory location. Right, no, so that program will actually misbehave. So let me correct it. I'll first see if you want to make it equivalent to the earlier program, then what I have done is not correct. I think it's a slip, cut and paste mistake. It should be star p plus plus equal to I star I period. So this itself, this statement itself increments p. If I add that p plus plus here, what I am doing, you are right, and I am doing something wrong also. So alternate location, maybe 0 I put here, and then in 2 I am putting 4 and so on. So there are a lot of incomplete or garbage elements in my collection. So I really did not want this. Ignore this. If you want every location to be initialized, then what I have written here should be correct. So your statement is right. Yes, I am only initializing alternate memory locations. The code as given will do. Somebody asks Rupesh Sahu, what is L value? So again I will say L value basically is address of some object X that you have created, where X is a variable. Okay. So if you write, for example, float x equal 2.0, the way I will try to treat you this whole thing as the r value of x is 2.0. So what you store here I will call as r value, the value of this object, the name of the object is ampersand of x. And you know that 5000 is a gross simplification by me. The actual addresses are 0x and a huge number after that, which is the real address. But I am taking this as decimal simple address. So coming back, L value is the address of an object, R value is the value of the object, and there are other attributes like type, local, global, register, whatever. So I hope you have got this 2 and 4 byte stuff. For anything that you have a confusion, double, a struct, an array, please say size of and the name of the entity, and it will show you how much bytes have been allocated. So null pointer is not same as initialized pointer. Null pointer says it is the address 0, okay, or null, and it has to be initialized properly. Okay, huge and far pointer I will skip here because I am not going to look at it. Okay, this is not really part of my course. I will not be requiring it. I don't want to confuse others. What is a wild pointer? So these are all loose terms. Don't take them very seriously. So typically, if you have a pointer p, okay, remember pointer p is supposed to be an address. So here is an object x. I don't know what x is. You are supposed to put the address of x and then it becomes a proper pointer. But what if so happens that I have taken this p and right now it is pointing to nowhere? It can happen somewhere. Nowhere of, which means not to any object of interest to me. For example, if I take this p, suppose the size of x is b bytes, and I do p equal to p plus b for whatever reason. So my pointer is somewhere here. It is beyond x. So I don't know what this pointer is doing. It's a wild pointer or a pointer which points to nowhere. Dangling pointers I'll come to later, so I'll not confuse you. A dangling pointer could be a worse thing in some sense, which will come when I deal with linked lists. So let me defer this dangling pointer business. This I have to do when I do heaps and runtime memory. I'll give you a proper and correct example. So I'm skipping huge and far pointer because it's not relevant. Dangling pointer I'll come to in the next lecture. How many types of structures available in pointer? This question is not clear to me. How many types of structures available in pointers means what? Okay, so let me interpret the question in some way because I would like to answer. I have still a few minutes. So I assume that this question means what type of structures a pointer can point to. I don't know. This may not be the correct question. So this is the question. I will give you a more generic answer. Don't worry about structures at all. Any data structure that you can create, that you can write in this language, any data structure, a tree, a graph, a tree of trees, a list of graphs, I don't care. Any data structure D that can be created. I have not told you, of course, how. In C, you can have a pointer to it. Anything that you can create, you have an address and therefore you can create a pointer. So no matter how complex your structure is, for example, I can have, just to draw something, an array of pointers. This points to something. This fellow is a structure, okay, so it has some irregular element. This fellow is a pointer, which again is an array. This fellow again is a structure. Anything is fine, and I can have addresses of all of them. Okay, so there is no limit to how complex a structures you can define, because the language has given you full flexibility of defining anything that you want, nonsensical or otherwise. So anything that you can design, a data structure, you can create a pointer because it is stored, it has an address, and therefore a pointer is possible. Anything that you store, a pointer is always possible. So there is no limit to the number of types according to me. Does type def, questions are not clear. Does type def work with void in this format? Absolutely yes. You want to create a function which returns void, just you replace void by the return type, it will definitely work, no issues. How much memory will be consumed by int star A? Now this is a tricky question again. You may say your sir said something and Vishwa says something. So the recent RAMs have increased in size, you know, they are gone into almost terabyte ranges. So int star is not important, float star is not important, anything star, any pointer is typically given 8 bytes today, not in old systems. Because through 8 bytes you can address RAMs of size in terabytes. What does it mean? If you want to address the last byte in a big RAM, you need 8 bytes of space to store that point. So it doesn't matter what you are pointing to, whether you're pointing to a structure or an array of structures or whatever, a pointer is just an address, independent of the object. And the largest address that you have in your memory determines the size. Since today we have already reached here, all old codes have been rewritten with 8 bytes as size of a pointer. So you can check out, all you have to do is do a size of whatever you want, a pointer, and you will get the answer of any pointer or pointer to any object. Word pointer, don't worry, I'll come back to functions and I can do it. Can the size of a pointer variable be modified? I have said what is the size of a pointer variable. Size of a pointer variable be modified. So size is fixed to be 8 bytes. You can change that, but you can change the size of the object that you are pointing. How can you get address of main function? Very easy. Write a main and just say address of main. You will see the address. That's all that it requires. Is enumerated data type declaration get size of say size allocated? Okay. So enumerated data type, again you can figure out the size. What is enumerated data? It's a list of labels that you want. The only insistence is this should be finite. Okay, so you can have colors, black, white, gray, whatever you have. Okay, or you can have something else. So enumerated data type are entities in your domain, but they must be having ordinal values. So they are basically numbered from 0 to something. So what is your question? So the data size of an enumerated data therefore depends on the size of this collection. It's always a finite collection. So the compiler figures out you want 10 colors or you want 256 colors. You will look out the list, and this list size determines the size of the data. So this is fixed by the compiler looking at your actual description of everything that you have. So since you fully describe your enumerated data type, you enumerate it, the size depends on the size of the numbers that you have, the elements that you have put into the enumerated data. And since these are all encoded as integers, therefore it is like a list of small integers. Okay, I think the next class people are ready, so I should now be quitting. So I hope I have explained many of your questions. Feel free to write on the forum, which I think remains live, and I can answer more questions. And we'll meet next Friday, same time.